Hey there, this is Mr. Wilford, and I just wanted to go over Section 2, Chapter 4 with you, multiplying matrices. If you remember in the last section, we defined what a matrix was, and we were able to add and subtract them. And we even took a scalar number, which was just one single number, and we multiplied that by a matrix. In this section, we want to be able to multiply two matrices together. And this would be a matrix product would be our answer that we get out. And one key thing that you want to do before you actually even start multiplying matrices is to check to see if you are able to multiply them at all. Um, and what you have to check is, if you remember, we talked about rows and columns in a matrix in the last section. What you have to check is the number of columns. So here I have three columns, they go up and down, uh, must be equal to the number of rows in the second matrix. If these two numbers are equal, then you can multiply them, and your answer that you would get out actually comes from these numbers here. The dimensions, it would be a 2 by 4 matrix that you get out. If you look over here, these two matrices C and D, if you notice I have two columns in the first matrix and I have three rows in the second matrix. So that would mean I would not be able to multiply those two matrices, and then I would just be done. I would just say that it's not defined or not possible. So some of the problems that you're going to be looking at in this section will look like this. You'll have to decide if you can or cannot multiply them together. For example, here in example A, you're looking at the columns and the rows, and if those two numbers are equal, then you can multiply them, and your resultant matrix would be a 2 by 3 matrix that you would get out. Over here, the columns of the first is not equal to the rows of the second, so you cannot multiply those two matrices. It is not defined. Now, in order to actually multiply matrices, it's a little bit tricky, and if you look at this short example here, what you want to be looking at is the first row and the first column. That's how you start out, and you're always going to be multiplying numbers and then adding them. So this example here is showing us we would take 1 times 5 and then 2 times 7. So we're moving over and down. You multiply those numbers and then you add those numbers together. Then you stay on the first row and go to the next column. So 1 times 6, 2 times 8. Then once you've used up all the columns, you go to the next row and go through the columns again. 3 times 5, 4 times 7, multiply and add. 3 times 6, 4 times 8, multiply and add. And when you simplify this part, that is your resultant matrix. If you look at example 2 here, it really does a nice job of putting it all together. Step by step, how you get your answer out here is the resultant matrix. And then a couple more examples there as well. And then here is example 3. It's an application problem. And then going down here we have something called a square matrix, and basically a square matrix is where you have the same number of rows and columns. So a 2 by 2 or a 3 by 3 is a square matrix. When we talk about a main diagonal, it would be this diagonal of numbers here, and if these are all ones and all the other numbers are zeros, we have what's called an identity matrix. And whenever you take an identity matrix times another matrix, you will get out that matrix. It's very similar to multiplying a number in algebra by the number 1. And then in the last slide here, we talk about powers of square matrices. Take a look here at what's happening. A squared, we're multiplying the matrix A times A. And with all of these matrices, if you take a look at a graphing calculator, if you have a graphing calculator, you can usually do a lot of these matrix multiplications on a calculator. So be sure to check that out and do a little research to see if you can figure that out. It makes it a lot easier. If you have any questions, please let me know. Thanks.